We're going to begin with phase transition of regret for logistic regression with large weights, presented by Tanmay Devale.
Yeah, so I'll be presenting the paper titled Phase Transition of Regret for Logistic Regression with Large Weights by Michael Drmota, Philippe Jacquet, Changlong and Wojciech Szpankowski. So this work focuses on in the online learning setting. So as a reminder, in online learning, there's an environment and a predictor. The environment produces some feature vector, and then the predictor gives prediction for it gives some prediction, and then the environment produces the true vector, and then the predictor suffers some loss based on some loss function. This work focuses on a fixed design online learning problem in which the feature vectors are revealed in advance, and the labels are provided in an adversarial fashion. So the labels are -1 and +1, and they focus on a class of logistic experts in which the weight vectors are bounded by some value r. And the goal of this paper is to understand how fixed design min-max regret depends on the weight radius r. So as we all know, regret is basically the difference between the accumulated loss of the predictor and the loss suffered by the best predictor in class. And so the fixed design min-max regret would essentially be the best possible regret obtained on the worst possible labeling. So the expected min-max regret would be taking expectation over all your possible feature vectors. So from the literature, it's known that if your radius is bounded, then the expected min-max regret scales as d by 2 log t. There is also a generic upper bound which grows as d by 2 log t r square by d, but the fixed design regret exhibits a fundamentally different behavior. So if your weight vectors are unbounded, then the expected min-max regret has a lower bound of d log t, d minus 1 log t, and we'll see that proof soon. And from Drmota et al, it shows that if r is of the order is less than t to the 1/4, then your expected min-max regret is of the form beta r d log t, where beta r is alpha by 2 plus 1/2, where r is t to the alpha. So the open problem from these two results asks for what happens if your r is between t to the 1/4 and infinity. So in this paper, they show that if your feature vectors are from an IID uniform sphere of dimension d, then your expected min-max regret is of the order d log t. So it completes the picture from Drmota et al for r greater than t and shows a sharp saturation of the order d log t and a phase transition when r is approximately equal to t. So from Drmota et al, it shows that beta, so your expected min-max regret is beta d log t. So for if r is t to the alpha, when alpha is less than 1/4, it says alpha by 2 plus 1/2, and when r is greater than t, alpha becomes 1. So the red dotted line is the conjecture from this paper. They hope that is the way it behaves. So the key technique which they have used in this paper is to reduce your regret to something known as the Strakov sum. So which is basically summing over labelings of the best likelihoods achieved by some weight vector w. So due to the way they have defined the loss function in this problem, your regret would become log of your Strakov sum, and therefore if you bound your Strakov sum, you can bound your regret. And they show that the expected Strakov sum is of the order t to the d. So they use this technique known as a splittable sequence. So basically a splittable sequence says that so a labeling sequence is called splittable if there exists a weight vector which predicts in that particular direction. So for an example, if you look at this figure, let's say you have these four, you are working with R2, so your weight vectors belong to R2, and these are your three instances, 1 by root 2, 1 by root 2, -1 by root 2, 1 by root 2, -2 by root 5, and 1 by root 5. So we look at the lines indicate the solutions for xt comma omega w equal to 0. And therefore, if you notice, there are 6 possible labelings that are achievable in this particular paradigm. So instead of 8 possible labelings, so only 6 are observed. So therefore, in general, if your xt is in a general position, your number of splittable sequences are of the order t to the d minus 1. So we can use this fact to obtain an immediate lower bound. So your log stack of sum can be lower bounded by restricting to the splittable sequences. And in the splittable sequence, as there exists a W, the supremum is achieved. So this essentially becomes log of the number of splittable sequences. Therefore, we get a lower bound of the order D log T. So on a high level, the main obstacle in bounding the likelihood is that the maximum W depends on X. So the supremum is strongly connected with your data. To break this dependence, they discretize the parameter space using the splittable sequences. So for the lower bound, they use packing, where they replace the continuous supremum using by a finite set of well-separated candidate directions, and upper bound the maximum using the supremum, then use linearity of acceptation over the fixed W terms. Whereas for the upper bound, they use covering. Each direction is close to some cover point, and geometrically, every cover neighborhood intersects only polylogarithmic number of regions. So therefore, the overcounting is not by too much, and therefore, after they discretize, each term has a clean product form, so they can bound the expectation analytically. So they use packing for lower bounds and covering for upper bounds. So therefore, in this paper, they complete the phase transition picture for R greater than T and identify covering and packing as the core geometric mechanisms. And they pose an open problem as to what happens in the intermediate region where R is between T and T to the 1/4.
Okay, thank you for the nice presentation. We have time for quite a few. We have time for more than one question, actually.
I'll try to answer, but yeah.
So I was wondering if you know, like, where the proof breaks down when you go to this open regime, where the current proof doesn't.
I'm not aware of what exactly happens in that regime. Sorry.
Okay, thanks.
Okay, thank you. Thank you for giving the presentation. Okay, the next presentation is by Gilad Karpel on optimal L2 regularization and high-dimensional continual linear regression.
So hi guys, today I will be presenting our work, and namely optimal L2 regularization in high-dimensional continual linear regression. So we start with a bit of introduction about continual learning. Unlike standard learning, where you're given a data set X and labels Y, and you're supposed to kind of learn a model that can predict accurately Y given the data set X. In continual learning, the learner is exposed to T sequentially tasks. At each iteration, the predictor is updated using only the current task, but it doesn't have any access to previous tasks. Naturally, one of the main problems that may arise in continual learning is upon arriving in new information, the model tends to forget previously learned tasks. I think this figure can illustrate this effect. So upon learning the first task, the model is able to predict accurately between the samples in orange and the ones in blue. Upon arriving at the second task, it kind of overfits the second task and thus forgetting the first task. While in the ideal case, which is what we aim to get, we essentially get a perfect predictor of both tasks. So in order to mitigate catastrophic forgetting, it is common to add regularization towards the last predictor. This way, you kind of do not forget entirely about the past. So indeed, in our work, we consider the following algorithm, namely continual linear regression with L2 regularization, where the entire regularization term is decided by only a single parameter. While this idea may look simple, recent empirical findings found that it performs similarly to standard baselines. Sorry, can you guys? Okay, sorry about that. Now you can hear me fine. Yeah. Okay, good. So our main question in the paper is to ask ourselves, what is the optimal regularization strength? Or at least if we can't answer this, how does it scale with the number of tasks? So even finding the answer to the second question can help reduce computational cost by first finding the exact scaling over smaller task horizons, and then adapting the same scaling for longer task horizons. So we first need to consider some statistical setting. We consider independent random feature matrices having IID random entries with mean 0 and some variance V of x. We consider high dimensional regime where n, the number of samples and the dimension is are both going to infinity, while the ratio converges to some alpha, which is less or equal than 1, which means that we are in the over-parameterized regime. We consider noisy labels coming from a linear model where the label is decided by some teacher. The label equals to the data times the teacher plus some noise, independent noise, having a mean 0 and some isotopic covariance, specifically as V of z times identity. We focus on the generalization loss, in which we define as the mean expected distance over the current predictor over all previous teachers. This essentially can be shown using our statistical setting to be equivalent to minimize the MSC using some testing data. So our first contribution is to give exact generalization analysis. We essentially give explicit generalization loss for all task horizons using any regularization parameter greater than 0. While we don't give the explicit value here, we do note that this can be decomposed for 4 terms. The first one is the label noise term. The second is the teacher variability term. Third one is the interaction term. And the fourth is the temporal teacher correlation term. One of the main tools into giving the explicit expression for the generalization loss is to use the Marchenko-Pastur law, in which we take the resultant matrix and then replace it with its deterministic equivalent. So using the exact generalization loss, we can derive the optimal regularization strength. So in order to do this, we will need to assume something about the teachers. So our assumption is that the teachers are drawn IID with some distribution having mean W star and the covariance metric sigma. This assumption can be generalized to teachers that are coming from independently from perhaps some distributions, but the some distribution must have the common mean W star and the same covariance metric sigma. So a theorem states that lambda star, the optimal regularization strength, is asymptotic T over ln T, or more specifically, for all epsilon greater than 0, there exists some threshold, which is asymptotically O of 1 over epsilon squared, such that for all T greater than this threshold, the optimal regularization strength is some scalar up to some epsilon accuracy. We know that when V of z and trace sigma are simultaneously 0, then it holds that lambda star is going to 0. This is the noiseless single teacher case. So we verify our key theoretical result using some experiments. So first we consider MNIST as a binary classification problem where the digits of 0 to 4 are converted to class of 0, and the digits of 5 to 9 are converted to class of 1. We consider 2 models. The first one is the linear regression, and the second one is the neural networks experiment. We train with mean squared error, and then we give our results using the 0-1 classification error. The teacher, we consider 2 types of teachers. One of them is the single noiseless teacher. The second one is multiple IID teachers. The noisy labels are implemented as each label is flipped IID with probability of 0.2. So our results. the star point marks the minimum over the regularization strength. We can see essentially that indeed we have some near linear scaling of lambda star in the task horizon. And it seems to hold also in a much more challenging neural networks model. Yeah. So let's summarize. What we do here is to give exact analysis of the generalization loss. This can provide insights to how to choose the regularization parameter for any teacher setup. We find that the optimal scaling in a simplified linear setting is T over ln T. And this was supported by experiments, even when our assumptions do not hold, such as MNIST data, which is finite dimensional and of course doesn't have isotropic covariance. And this seems to hold also in much more challenging neural network setting. So for future work, one can relax the IID teacher assumption. We did something similar in a paper we submitted to ICML, in which we gave contradiction to our analysis that we made here using some other teacher model than the IID teacher assumption we used here. One may consider non-isotropic covariance metrics, but we do note that this is highly non-trivial and almost impossible. If someone would like to discuss it, I will be more than happy to discuss about it. And analyzing nonlinear models, once again, we also consider this to be highly non-trivial. I actually don't know any related work doing something similar, but once again, I will be happy to discuss about any future work if you guys have any ideas.
Thank you for the nice talk. We have time for a couple of questions.
I had a question, actually. It's something that you had on slide 4, which was like about, you said that L2 regularization performs similarly to simple baselines or something to that effect.
To standard baselines.
To standard baselines, yeah. Like, what does that mean? Like, what are standard baselines? Are these other methods for continual learning or what? Like,
yeah. The regularization term can be non-isotropic. It can be, depends on the direction. So they measured it with, wait.
don't worry too much about it.
Yeah, so they measured it with standard baselines. They included synaptic intelligence and elastic weight as EWC. Which you may know, but these are considered standard baselines, which are used widely in the empirical research of continual learning.
I see. So L2 regularization may be a simpler way of doing regularization, maybe.
Yeah.
Cool. Thanks. Anyone else?
Okay, let's thank Gilad for the talk again. Yuping Zheng on quantitative convergence analysis of projected stochastic gradient descent.
Good morning, everybody. And I'll be talking about quantitative convergence analysis of projected stochastic gradient descent with the Goldstein subdifferential. This is a joint work with my advisor who is in the audience today. The first of all, projected SGD is used to solve the stochastic optimization problem. In our work, we specifically assume the constraint set X is convex or compact, and the F bar is smooth, but possibly non-convex. Specifically for the external random variables, we consider they can be sub-Gaussian or mixing data. So we also consider general step size as long as they're less than 1/2, with specific result for constant step size and assumptions under standard stochastic approximation conditions. So why do we want to study the convergence of project SGD? First of all, SGD is everywhere in machine learning, and the projection is try the when we complete the algorithm updates, we basically introduce the convex projection, and they are good to stabilize the algorithm, etc. But the highlight here is we found there's still some gaps despite it has been studied for a long time. The main thing here is there are two kind of existing convergence criteria for a non-convex projected SGD. The first one is gradient based on gradient mapping, but we found but they requires a variance reduction technique like mini batching to achieve a low error. The second kind is Moreau envelopes based. They do not reduce to the unconstrained measure, and at a higher level, we want to say the presence of both constraints and the stochasticity introduce challenges to the convergence analysis. In this picture, we can see when the X star, the green dot, is the local minimizer, and we obtain the distance between the negative gradient to the corresponding normal cone is 0. However, if we perturb the green points to the red point, and then you can see the negative gradient is no longer overlap with the normal cone, and these difference can be problematic for stochastic algorithms. So this is some illustration about a Moreau envelope. It is basically a smooth approximation of non-smooth function. So you can see the the blue line curve there is the original function, which is bounded between -4 and 4. And the orange curve there is the Moreau envelope, which is smooth, the original one is not smooth around the L boundary. And with a very simple example, here we can see the gradient of the F bar is different from the gradient of the Moreau envelope. And this is the issue I mentioned earlier, that this kind of convergence measure, they cannot directly reduce to the very commonly seen norm of gradient convergence measure for an unconstrained problem. On the other hand, the gradient mapping-based method, they can indeed reduce the norm of gradient. However, we cannot, on average, we cannot achieve a low errors or low errors unless the variance of the random variable is reduced. So, motivated by these limits, we propose the new convergence measure, which is the distance between the negative gradient to the so-called Goldstein subdifferential, which is a relaxed version of the Clark subdifferential. And in the special case, when we see the indicator function for the constraint X or the Goldstein subdifferential, the Clark subdifferential, and the normal cone, they are the same. So from very similar picture here, the X star is still the local minimizer, but now if we perturb it to the red point, we can see the negative gradient actually locates inside the Goldstein subdifferential. So this basic idea is saying the Goldstein subdifferential is to approximate the normal cone, and which introduce the flexibility or to tolerate the perturbations. And we can see here, actually every point is inside a red circle. They actually share the same Goldstein subdifferential. So this is a convergence measure. And this is three types of assumption we impose for the random external random variables. The first kind is a subdifferential Gaussian subdifferential random variables, and the second kind is independent and the bounded variant with bounded variance, and the third one is a variable called L mixing processes, which is basically a quantitative way to measure the time dependencies over time between the random variables. So for the result, we here only present the result for the constant step size. We also have the result for the more general step size mentioned before. And here on we can see the error bound for the expectation of the distance is of order of n to the minus 1/3 with properly chosen step size. And the BK here I'll explain in a little bit in the proof idea. The next part of the result is we show specifically for sub-Gaussian assumption with high probability we can have an upper bound of order of n to the minus 1/5 or up to some logarithmic factor. So here's some kind of a high-level overview of the proof idea. The key is the so-called continuous time approximation. So we separate the entire time interval into multiple sub-intervals in a careful way that gives you all the breakpoints, and then we introduce this series of continuous time process which starts at each of the breakpoints. So you can see from the simulation, the projected SGD starting from the same initial points, they can actually diverge because of the non-convexity of the objective function. However, I don't know if you can see the projected SGD will stay close to the dotted line, which is the jump process, basically the process jump between all the continuous process. So the BK now here we see is the distance between the jump process and the algorithm. And the key takeaway here is that we can show that at infinite time, the two processes they are actually close with probability 1. So here I will summarize the work. First of all, we propose a new convergence criteria, and this allows a direct comparison with results on unconstrained problems, and it does not require variance reduction techniques. And the results holds in both in expectation for both IID and mixing data. Besides, for the special case of IID data, we have the first non-asymptotic high probability bounds for the non-convex projected SGD. So in the future, we do want to check why our bound is not as fast as those in the those Moreau envelope-based result. And besides, it can be interesting to study the adaptive step size rules. And potentially this new convergence measure can be used for policy gradient algorithms within the actor-created reinforcement learning algorithms, because sometimes you have to impose constraint for stabilized controllers. Yeah, and this is of my talk, and I'm happy to take any questions.
Thank you for the nice talk. We can take a couple of questions. Okay.
So okay, so the central contribution is this one that you're changing the criterion that you put in the theorems, which is that instead of just controlling the norm of the gradient squared, you're controlling this approximated, this like smoothed differential. So whereas other papers, they either smooth the objective function or they sort of smooth the method by smooth the stochasticity by using mini batches. You've actually smoothed the objective that you put in the theorem statement, which is you have this Goldstein differential, which with the epsilon, which is like a smooth subdifferential criterion. Yeah. Okay. So one thing I wasn't still sure about was how the stochasticity is handled throughout the proof. And one of the things I was wondering, you didn't list it in your open problems, but do you think that a high probability proof would go through cleanly? Because that would be one way to test if sort of this technique is robust to, handling very noisy stochastic gradients and not having to use mini batching.
I think I'm a little bit confused about what you mean by a high probability proof will go through. What does that mean? Go through what?
Yeah, so your proofs were an expectation.
Yeah, there's also a high probability result.
Oh, there was.
Yeah. Sorry.
Okay.
Right. Yeah, we introduced the Q function as a polynomial, polylog function. It's a high probability result.
Okay, my bad. Yeah,
No problem.
I missed that, but it. Am I losing? I mean, it's not. It doesn't scale with log 1 over delta. Oh no, it is. If you set
It's
alpha,
over
okay,
here.
if you
The
set
delta
alpha.
hat, but the delta hat itself is the delta over the alpha.
Yeah, sorry, I missed this. Okay.
Yeah.
Okay, so you're basically the message of the paper is that it is enough. You can remove a lot of the complexity and a lot of the issues of previous papers just by changing the left-hand side of the bound to be this Goldstein differential, and you don't have to worry about a lot of the other things, and you still get the log 1 over delta bounds. And
I think so. And the thing is that because I mentioned the issues with the previous, yes, we can get rid of those annoying things. Yeah. Thank you very much. Yeah, and thank you for the summary. It's good.
Variance reduction and low sample complexity in stochastic optimization via proximal point methods, authored by Jiaming Liang, presented by Matthew Burns.
So unfortunately, Professor Liang couldn't be here today. So in his stead, I'll be presenting the work that he submitted at this conference on stochastic approximation methods via proximal point analysis. So our problem of interest is stochastic convex composite optimization, where our objective function phi is the sum of two functions f and h, where we assume f is mu strongly convex and L smooth, and h is merely closed convex, but we assume it has some proximal mapping. So f is your loss, h is your regularization term like L1 or L2 regularization. We don't have access to deterministic oracles, so instead we have stochastic oracles capital F and little s, where f is an unbiased estimate of our function value, little s is an unbiased estimate of our gradient. We assume that little s is has bounded variance, and for simplicity, we assume the domain of h is bounded with some diameter d. So standard folklore and stochastic approximation, if we were to merely apply stochastic proximal gradient methods to this problem with sufficiently small step size, we get an epsilon small primal gap in this many iterations where we have our problem dependent term kappa, which is the condition number, specifically of f, and then we have our variance dependent term. If we want to get a high probability result with that, just using Markov's inequality, we pick up an extra factor of 1 over p. That's not great. We don't like that. So we want to turn that to log 1 over p. The traditional way to do that, as we saw in the last talk, is to add a sub-Gaussian assumption on our noise. So we assume that S is a light-tailed distribution. This holds if S truly is Gaussian or if it has bounded support. But for heavy-tailed noise that we see in machine learning, that typically doesn't hold. So we want to remove that assumption. The alternative to making stronger assumptions on our problem is to make the algorithm itself more robust. So a quick preview of the results that we did in this, or that my advisor showed in this work, is that to get this epsilon primal gap with 1 minus p probability, we effectively turn the 1 over p dependence to log 1 over p. We unfortunately pick up an extra factor of kappa, but this is still an improvement over the previous bound. And there's 3 main ingredients to our analysis or to our algorithm. In the outer perspective, we use an inexact proximal point method. To solve each proximal subproblem, we use a stochastic approximation method based off of a single cut bundle model. And then these by themselves will only generate low probability guarantees. So to turn that into a high probability guarantee, we use a probability booster, similar to patterns that we've seen in previous talks. So quick overview of inexact proximal point methods. On every iteration, we're going to try to solve a problem of the form here, where we have our objective plus a quadratic regularization term, where xc is our proximal center. We can't solve this in closed form. It's as hard as the original problem in general. So instead, we replace f with some tractable model fj, which we can solve in closed form. The typical choice for this, or atypical choice, is a cutting plane model where we take all of our previous iterates xi, linearize f, and then maximize over it. This is called a multi-cut model. And as you do more and more iterations, you get a better and better approximation of f in the neighborhood of your point of interest. However, the stochastic setting adds some difficulties. So just straightforwardly applying Jensen's inequality, the expectation of a max is lower bounded by max of expectations. So if we examine our model gamma and f, we actually no longer have that gamma is necessarily a lower model for F, which we need to do good convex analysis. So an alternative to using a multi-cut model is to use more modern alternatives. So for instance, a single cut or a two-cut update. I'll focus on the single cut update because that's what we use in this work. By the way, whenever I say we, replace that with my advisor. We is just faster to say. So we use the single cut update where we just aggregate one single linearization. And you can straightforwardly show by induction that as long as your initial model, gamma 0, is a lower model for F, your future updated model after doing the convex combination is also a lower model for F. So we can use this for stochastic approximation. So using that, we define our proximal subproblem solver, PSS, as follows. So for a fixed number I iterations, on every iteration, we take a sample of our stochastic gradient, incorporate it into our dual average, do a proximal step, and then we do a primal averaging step. And then after I iterations, we output the last exact minimizer, xi, which is the exact minimum to our bundle model, and yi, which is the final primal average. So we have some convergence guarantees for this proximal subproblem solver. So this quantity ti, I won't get too into the details, but it upper bounds the primal gap for our proximal subproblem. And assuming alpha, our convex combination parameter, is sufficiently large, then it goes to 0 in expectation. And we have a very interesting kind of decomposition here, where you can view this first term as sort of a bias, the second term as a variance. And unlike, for instance, SGD, where you just have this lambda sigma squared, where you just have to take lambda small, we achieve a variance reduction by a factor of I by doing multiple steps. So translating this back into the outer IPPM perspective, our goal on each iteration is to solve a problem of this form by exactly minimizing our bundle model, where gamma is the bundle model from our last iteration from PSS. So choosing ZK as our exact minimizer X, WK as our primal average Y, translating the previous slide into our outer notation, or outer loop notation, we have this guarantee where epsilon is the term we showed before. Then doing some more analysis with a probability at least 3/4. We have our proximal primal gap plus a quadratic regularization term is order epsilon. Using this, we could get a global convergence bound, but with very low probability. So we get that primal gap is order epsilon with probability 3/4 to the k. This isn't sufficient. So instead of directly solving it using ingredients 1 and 2, we introduce a probability booster where we query the PSS n times to generate n pairs, each of which satisfies this low probability bound, and then feeding them into a clustering technique based on robust distance estimation. We turn that epsilon 3/4 guarantee to a kappa epsilon with exponentially decaying or exponentially increasing probability in a number of samples. So for those of you who aren't familiar with robust distance estimation, it's essentially a generalization of median of means to a generic pseudometric space. I won't get into the details, but I refer you to the main paper. It's a really interesting idea. So our probability booster is built on a second tertile selection. So roughly speaking, we generate 3 index sets. So J1 is our first index set, which is the set of indices where our pairs Wj are close to our minimizer in Euclidean distance. J2 is the point where Zj is close in Euclidean distance to our minimizer with high probability. We then take something in their intersection or an index in their intersection and get a high probability epsilon estimate of our subgradient or gradient of F. We define a metric DH to account for our composite geometry, and then generate a third index set to get the set of Wj's, which are epsilon close with high probability in this pseudometric. And then we simply pick an index in their intersection, which we show in the main paper is non-empty. So there's a pair that's guaranteed to satisfy all 3. So as long as we take sufficiently many stochastic gradient samples and a robust gradient estimation, then we get our high probability result where we have a kappa epsilon bound. So combining all 3 ingredients, we have our stochastic proximal point method, where on every iteration, we query the proximal subproblem solver n times, feed those into the probability booster, and then we get a pair out. Z bar k is fed into the next proximal subproblem solver as the prox center, and we show convergence in WK. So differences from prior work. So prior work from Davis and colleagues they just merely assumed theoretical proximal oracles, whereas we provide an explicit implemental subroutine. They have to assume a linearly decaying step size to show convergence, whereas we show a constant step size subject to a condition on mu. And it's because they use a classical Rockefeller type IPPM analysis, whereas we use a more modern HPE-like modern IPPM analysis, which allows us to do away with the linearly decaying step size. So main result, simply combining the outer complexity K, the inner complexity I, and log 1/p samples per step, we get the claimed complexity. I'll refer to the main paper for the details here. So in conclusion, we propose a bundle type stochastic approximation method for stochastic programming. It's a single cut variant which aggregates all previous information in the dual, and it effectively achieves variance reduction and low sample complexity for high probability results. There's a few extensions for future work. So for instance, adaptively choosing our step size and iteration count to remove that kappa overhead. Our parameter selection requires knowing the smoothness and strong convexity. We'd like to do away with that with an adaptive method. And then potentially exploring other subproblem solvers such as Nesterov acceleration with restart would be a direction for future research. Thank you.
Thank you for the nice talk. We'll take questions if there are any.
A question about the probability booster.
Yep.
If that was a part that need any assumption, or it could like work on any stochastic model.
As long as your samples are IID, I believe it can work on anything. I think it might require bounded variance. I'm not sure. This is the part I'm most hazy on, but as long as your pairs are IID and you have some bounded variance, I think it should work. Well, and also like all of your pairs need to have a probability over 1/2 of being epsilon close to your minimizer. So like there are conditions on these which you need some subroutine to satisfy.
Okay, let's thank the speaker again for the nice talk. Speaker is Clement Lazane, who will present accelerated mirror descent for non-Euclidean star-convex functions.
So thanks everyone for coming to the talk. So I'm Clement. I'm doing a postdoc at Toulouse. And today I'm going to talk about a work I graduated from a PhD last year. And I'm going to talk about a topic I focus on at the end of my PhD, which is acceleration. So it's a joint work with Sophie and Walter. They were my former PhD supervisor. And yeah, let's get to the talk. So the paper itself is quite technical. So for every written detail, I invite you can directly ask me the question or check the paper. I will try to give an overview of all the technique and the insight of we had writing this paper. So first, let's define what's like acceleration. So the idea is that we are interested into an unconstrained problem, minimizing a function over a finite dimension space. And then like when you talk about accelerated method, there are many of them, but like the two main idea comes is like the one from the heavy ball methods, when on top of computing the gradient descent, you also add the momentum factor depending on your previous iteration. And then there's the alternative way is the Nesterov accelerated gradient. And it's instead of taking the gradient at the previous iteration, you take it as another smarter point. So which is also referred as the optimistic way of choosing it. And this is the acceleration that we will talk about. And the idea is that, okay, so why do we do acceleration? The general idea is that when there are two very important assumptions to make accelerated algorithm. The first one is often your convex need to be convex. And the second one is that your function needs to have Lipschitz gradient, such that the intuition is that you could like somehow predict what the next gradient iteration is going to be. And the consequence of that is that when you study a problem like that, then the convergence rate goes from 1/t to 1/t squared. And I precise that here we are supposed in the high dimension where the dimension d can actually be bigger than t. So the idea is that, yeah, really like which kind of result, convergence result we could obtain. And then another ingredient that's important is that when it comes to question when it comes to function with non-Euclidean geometry, which means, for example, having Lipschitz gradient not with regard to Euclidean norm, but to a LP norm, or like in a constraint setting, it is often one of the extension is to use mirror descent, which is written in the following form. Is you are minimizing, so nabla f is your gradient, but you also consider deep C x xt, which is a sort of a distance. It's the Bregman divergence according to the psi function, and psi needs to be convex. So this is a very frequent technique we use to for the actually to do mirror descent, to do a gradient descent method on non-convex on constraint setting or non-Euclidean settings. And okay, so that was all in the literature, and let's say what's about new about our work. So we study in the star-convex functions. So the idea is that, so as I said before, non-Euclidean method we know a bit, but non-convex method we know much less about auxiliary method. And so one of the relaxation we took for the convexity is to suppose our function to be star-convex. So suppose you have like, so the idea is that we still suppose you have a nice minimum, which is x star, and that every time from each point of the space, when you look at it, the gradient somehow points at the minimum. So the idea is that when you do the scalar product between your gradient and the distance to the vector that point to the minimum, is always positive. Now we suppose if tau is larger, let's suppose it's always true. So when the function is convex, it's always hold for tau equal to 1. And yes, the idea is to like study convex function with little bit of perturbations. But the idea is that, okay, so does it make a problem much harder? And I say yes, compared to the standard accelerated framework. Because if you think about like a space with like n points, then convexity always refer as pair of points. So we'll have n squared constraint on the space, whereas we've seen the before in the star convexity is only have On of constraint because it's only referred to one point is fixed at the minimum. And on top of that, a lot of techniques such as like I forget the name of this nice Jensen inequality. Things obvious that Jensen inequality will not work. So a lot of the method need like to be reformulated very nicely. So the key point that was that allow us that gave us inspiration of studying this function was a Hinder paper in 2021. And then they suggested actually studying a PDE function in one dimension to select a very tricky point for the iteration. So as I said before, one of the key Nesterov accelerated method is to choose gradient at the smart point. And what Hinder did very great here is that they say, oh, the smart point is actually should be chosen by solving a by solving a PDE on the one dimension. The idea is that at each iteration, you keep those parallel computing as xt and yt. And the idea is that you simply just look at the function, how it behaves over this line. And if it turns out that one of the points that you find satisfy the following PDE, then it will satisfy very nice property that allow you to do the accelerated framework. So the idea here is like h of t of lambda is like the median point with weight lambda, and then yt is one of the extremity point. And yeah, so so here the plot is that because you can see that by the definition at lambda equal to 0, it needs to be equal to lambda equal to 0. If you take the opposite side, if you suppose by observe that such a point does not exist, then you realize like as lambda equal to lambda equal to 0, you will have like ht of lambda equal to 1. Then your derivative needs to be positive, and at lambda equal to lambda equal to 0, your ht of 0 needs to be bigger than positive. So at some point you will need to go under the curve, and that will give you a point such that it's the sum of the two terms is going to be negative. And the idea is that you actually can find such a point in a logarithmic time, that depending on epsilon. So which algorithm do we have for the two accelerated function to design accelerated algorithm for star-convex function. Well, there are actually 3 steps. The first one is solving the PDE we said before, choosing the correct lambda t, and then this will be like the right median point we choose between aggregated point xt aggregated and xt. So those are the xt yt I mentioned before, and then you do the mirror distance step, which is that once you choose a nice point, you choose the mirror distance step. And then you also do the last step is you do a steepest descent. So the steepest descent is a little bit similar to the mirror descent, but the main difference is that instead of considering the Bregman divergence, you will consider the norm in some powers. So it's a steepest distance because it's actually choosing the gradient direction where you minimize the distance as you travel for the norm. And then, okay, so what does it give in the end? So, for example, if you look at the function that are weakly smooth, and with regard to a p-norm, so on top of that is our upper bound, and the lower part is the non-lower bound for the convex function, actually, not star-convex function. We noticed that except the tau factor, like most factors are actually matched with each other, which means that 2 things. The first is that star convexity is actually quite a strong condition in the sense that the result we know for convex functions somehow still holds for most part. And the second part, yeah, so we actually did not lose any convergence result. We did not lose any information during our proof. We actually keep all the convergence sharpness, except tau need to be fixed later. Yeah, so as a takeaway message, so there are like 3 ingredients we have for like design a new accelerated method. The first one is the intuition says that the PDE equation we have was somehow linked to the momentum, because instead of taking the derivative of the distance function, you take the derivative of the objective function itself. So it somehow sounds like a smarter idea. And then the other 2 ingredients are like the accelerated mirror descent that's common in the literature, and then the steepest gradient descent, which seems very important for accelerated methods. And then for the future direction, there will be nice to know if this momentum effect is also present in other settings than star convexity, and also if steepest gradient descent can be done for another metric, because when the function is not smooth, but relatively smooth, we know that it's impossible to do any acceleration. But I was wondering if we can define a steepest gradient descent on top on a structure that is more general than a norm, where we can still do acceleration. Yeah, thank you for your attention.
Thank you for the nice talk. We have time for 1 or 2 questions.
I was hoping you could get an intuition on how your techniques or how the ideas of the paper allow you to actually handle star convexity. I ask this because if we're in the non-accelerated case, I mean, you don't have to do any math. It's just immediate that you're only evaluating point differences. But with acceleration, you have to compare on the xt's and yt's. So how is it you were able to convert all of the inner products with gradients into ones that use the reference point?
So actually the things that, so when it's convex, I mean, even for the convex K, when Nestor proposed it, it was very confused as a method. And one of the way of seeing it is to write it down in the online learning setting and talk about the regret and saying that, oh, it's maybe 2-player, like what's...
That's classical, that's Zheng's proof, but I'm still... That proof also still uses the multiple reference points, so I'm still not seeing.
I think the intuition behind it's really this steepest gradient descent where you choose because in our setting we actually suppose that your problem is unconstrained, and actually this only the last step really need the problem to be unconstrained, because we suppose that the xt plus 1, this last step is found on the open place where the gradient is somehow equal to, where the gradient with regard to this function will be equal to 0.
So you're saying if you don't do step, but I can do step 2 in the Q equals 2. Sorry, I'm just still not seeing how you're able to only rely on star convexity everywhere in the proof. So I'm just missing that.
Star convexity actually only refer to the step 2. I don't steps 3 and 1. They are. I'm just using the.
I guess we have to take it offline because I'm just super confused. I feel like I'm wasting everyone's time. So, okay.
Thank you again. The next paper is on DS-compatible log linear reliability with KL-Prox EM, presented by Alireza.
Thank you, everyone. Morning. I'm Alireza Abrahfroush, and I'm presenting on behalf of Shiva Krodi and Sravani Sovrupili. So you see, my name is not among the authors, so feel free not to ask any questions. Just kidding. And yeah, let's go forward. So this paper introduces a DS-compatible log linear parameterization for context-dependent reliability in a multi-annotator label fusion trained with a KL-proximal expectation maximization algorithm that provides provable monotone ascent guarantees. So let me start with the problem we're solving. And from now on, when I use we and our, we, I mean they and them and their. All right, so the core task is truth discovery. We observe noisy categorical labels from multiple agents. Think of it as an autonomous vehicles and roadside sensors at an intersection. And we want to infer the true label without ever seeing ground truth. So we don't have access to ground truth. The standard approach here is David's skin, which assigns a confusion matrix to each agent, and this static confusion matrix PI, and it uses expectation maximization to estimate it. So you see the equation on screen shows like PI of pi of agent A of I and J, which means what is the probability of agent A giving label I when the true label is J. So the problem with this approach is that this pi is the same regardless of whether the agent is 10 meters away from the object with a clear line of sight or 200 meters away with like through occlusion. So this leads to miscalibrated posteriors. All right, so to address the mentioned problem, our approach is simple. So we keep the DS confusion matrix pi as an anchor. And we learn a small log linear correction alpha from context covariates. So the key equation shows our context condition confusion matrix. So the numerator takes the log of the DS confusion matrix, which is the classic approach, and we take the log of the base confusion entry, and we add the correction, some correction alpha, and the exponentiates. So, and also the denominator is the actually a softmax normalization to make this and show like a probability distribution over all reported labels. And so, and also the this correction alpha comes from a three-layer multi-layer perceptron, and followed by a linear head. And we can see that, and actually, this correction kind of maps covariates to a shared representation, followed by these per-agent linear heads. So crucially, when you see alpha becomes 0, this pi tilde is reduced to the classic DS that we had. All right, so let's see here. In theorem 1, they established 2 properties. First, the validity of this probability sum, which for our pi tilde here if we sum over all i's, all different labels, for it equals to 1 for any kind of agent, for any sort of true label, and also any covariance. And the second one is what just I mentioned, when alpha becomes 0. So this automatically translates to the standard pi that we had. So this means that our model gracefully degrades to standard DS whenever covariates are uninformative. So you only gain from context, you never lose anything. All right, so let's say how we train our model. So we use a 3-stage procedure from A to C. In the first stage, we run a standard DS expectation maximization, and we when it converges, we reach to a baseline pi DS. And then stage B, we freeze our pi, and we train our multi-layer perceptron and also the heads against the DS anchor. So, and in the stage C, we unfreeze everything, and we alternate between E step, the gradient ascent on the neural heads, and we apply a KL-proximal update on pi. And the update rule shown here means that, okay, when we iterate, actually this iteration is proportional to the pi ds and also the exponentiated gradient over this tether strength parameter lambda ds. One of the things that this paper addresses is this identifiability of this approach. So Theorem 4 gives identifiability up to label permutation under 3 assumptions. So A2 requires diagonal dominance, which means each agent must be better than random, meaning the diagonal entry of the confusion matrix exceeds the sum of the off-diagonal entries in that column. This breaks the label symmetry. And A3 requires that the covariate features have full rank covariance, so there must be enough diversity in the observation conditions to separate the classes. And A4 is a mild non-degeneracy condition, so that together these all ensure that with sufficient data, the model converges to a unique solution. So do we have finite sample guarantees? In Theorem 5, they provide a pack-style bound, so the accessory scales as the square root of d prime times log k and d prime, and also the network parameters divided by n. So d prime is the hidden dimension of the multilayer perceptron, k is the number of classes that we have, and n is the sample size. This bound actually comes from Rademacher complexity analysis, and also the fact that the softmax is 1 Lipschitz, and the fact that MLP has bounded spectral norms. So with d prime equal 128 and n around 1000, this gives an actually informative bound confirming that training performance transfers to unseen items. Let's see the empirical validation here. So we validate on 2 data sets, V2X real, which has 3 agents, 4 classes, and 5 seeds, and full geometric covariates. The result table shows that our method matches DS accuracy, which is 0.9190 on test, while achieving the lowest variance among other seeds. The key win is the calibration, 12% EC reduction on validation and 8% reduction on the test. One thing that is important here is that geoheuristic reweighting with calibration enabled collapses to about 51% near random. So our softmax normalization prevents this. Also, on the second data set, OPV2, we transfer data set with only 2 agents and no calibration metadata. We still improve by 0.9% absolute over DS baseline. Of course, there are some limitations with everything, and the authors mentioned that these are the limitations of their model. So the main limitation first is if covariates themselves have systematic errors, like yaw drifting, time step bias, or the correction problem. So the correction heads can be missed. Also, the KL tether to DS mitigates this. The second one is if the items observed by only one or two agents have limited signal to separate reliability from class posteriors. And the third, our monotone ascent guarantee is for the EM surrogates, not the global optimality. The DS warm start helps avoid bad starts but it's not necessarily globally optimal. And for future directions, they suggest joint calibration, truth discovery estimation, online or streaming expectation maximization with drift detection, and also the extension to structural labels and detection tasks. Thank you so much.
Thank you for the talk. Any questions? Okay, thank you again. Oh, sorry. Okay. Okay, thank you again.
Thank you.